Hi. So far we have talked about network layer, and I'm going to be talking about the transport layer now. And we know that transport layer is responsible for end-to-end connectivity, and by end-to-end connectivity, you have to specify if you talk about end-to-end connectivity, you have to specify which process, right? It's process to process. So there are different processes, and those process each process will have a port number. Port number is represented in 16 bits, and with 16 bits you can represent 2 power 16 things. So that would mean that we have 2 power 16 available port numbers, right? Now there's a range of port numbers, and there's a range for famous port numbers, like famous services like HTTP, SMTP, or Telnet or FTP. Okay, these have famous port numbers. HTTP has 80, FTP has 21, Telnet has 23, SMTP has 25, and any of the famous port number you will find it in the range of 0 to 1023. Okay, uh, which and it's not really tough to remember it as well, because what is 2 part 10? It's 1024, right? So from 0 to 1023, it's 1024 numbers, and those will be assigned to the famous port. Those will be assigned to the famous processes. Then there's a reserved class, which is from 1024 to 49151. Now 1024 is just the 11th bit from the LSB, which is having the place value of 2 power 10. That will be 1, and everything else will be 0, right? And the 49151 would be the 49151 would be the 16th bit from the LSB. That's the most significant bit. If you take this, it's a 16-bit field, right? So the MSB would be 1, and the second MSB, second most significant bit, would be 0, and the rest everything would be 1. That's how you make 49151. So 49152, of course, is easier to remember. That would be the two most significant bits would be 1, and if else everything would be 0. So this is the reserved class from 1024. That is the place value, the bit which is having the place value of 2 power 10 uh, would be 1, and the rest everything would be 0. That's 1024 till 49151. That is the MSB would be 1. Except for the second, or you can just say except for the second MSB, everything would be 1. So that's 49151. That would mean that if the most if the starting two bits, if two most significant bits are 1, that is another class. Okay, so there comes the third class, which is for public use. So from here 49152 till the maximum, all ones in whole, whole all the bits 1, that would be 65535. Okay, till that is available for public use. Okay, so public, for general use. Okay, like anything. So this is about port numbers. That's about port numbers. Now the thing is that on transport layer a little bit, let's talk about what all happens, or let's just give what, couple of things that happens. So first of all, we've got protocols like TCP and UDP working on application layer, and they have certain ways of working, and we have preferences, where um, we have preferences when do we want to use, we have choices when do we want to use TCP and when do we want to use UDP. That's going to be, what kind of connection do we want. It'll be dependent on that. So we talk about transport layer. What all happens here? First of all, we know that fragmentation happens at network layer, because we make the fragments on the network layer and then give it to data link layer, that is the routers. And I mean, routers have 3 layers actually. The network layer does the fragmentation, and then it gives it to the data link layer, and data link layer passes on that fragment to other routers. through the link and everything. Now this happens because if at certain at certain router the buffer size was not as much as you expected, then you will have to, in between, if you're in between hops, you might have to divide your data packet into different parts, into different, into parts, so that it can be passed on, right? So for that matter, fragmentation is done. But the thing is that we do not want to do this. Why do we not want to do this? Is because our system is our system. The destination would be, a system as well, and that would be just one system. But a router is of, of more importance, because it is going to be used by a lot of people, and we do not want to, the bother the router that much with so much to do. It's already doing a lot. So for that, what do we do is we do segmentation on our part, and that happens on transport layer. uh, Now I've talked about ICMP, how we can find the maximum segment size. We just, we find out the MSS through that, and then and what is MSS is the bottleneck bandwidth, which of course, as the name suggests, what it is the least buffer size that would be available to you on any hop, either at the sender end, either at the receiver end, or at any of the routers. The least size buffer, whatever the least size buffer would be provided to you, that you will be having as your NSS, because otherwise fragmentation would be needed, would be, would be required, and we do not want certain situation, such kind of situation. So we do segmentation. And what else do we do at segmentation? When we do segmentation, we make a segment, right? And on each segment we add a header. And let's now talk about TCP header. So first of all, TCP header is, the least size of the TCP header would be 20 bytes, and the most size would be the, the yeah, most, right? Most size would be 60 bytes. Most size, the maximum size, what the fuck? Okay, so maximum size of the header can be 60 bytes, and minimum it has to be 20 bytes. So 20 bytes is the mandatory data, and the rest of uh, that's the options field, where you can use from 0 to 40 bytes, whatever, as much as you want. Not really as much as you want. You have to be, having certain, like, it has to be in the multiple of 4, because why we'll talk, not now. Okay, now 20 bytes is the mandatory field. Now you divide 20 and 5. 20 by 5, you get 4 bytes. Okay, so we have 5 rows of 4 bytes each, and one row is of 4 bytes. 4 bytes means 32 bits. So the first row would be we divided in 2 fields. One would be the source port, another one would be the destination port. What it is just suggested by the name itself. It's of 16-bit, both source port and destination port, and we've talked already about the ranges. And then we come on to the next row, which is sequence number. What is sequence number? Basically, we are sending a lot of packets, and we're also, receiving acknowledgements and everything. So sequence number the is the count, or is the actually byte number of the first byte of data that you have sent. Okay, and acknowledgement number, that's the third field, and these both are of 32 bits. So the second row is sequence number, the third row is acknowledgement number. Second row is of 32 bits, third row is of 32 bits. Sequence number is So sequence number is the byte number of the first data byte. Okay, an acknowledgement number is the data byte number that is being expected. Now what does that mean is that if I am a receiver, okay, I will look at the sequence number. I will look at the sequence number and I will get to know that which data byte is being, has been sent to me. Okay, so why would that be required? Is that I'm receiving segments and I may receive segments, in a random manner. So I have to know, that which segment comes after which segment. Okay, so for that matter, I would have to know that, you know, I would have to know the sequence number. So, and why do I not just say, the sequence number is 1 or 2, and this is the first packet, then that's the second packet? Why do we not say that? Because we do not say that because what if in between somewhere we did fragmentation? Now that data is being, has been divided into two different packets. Now there's nothing like, 2A and 2B, because otherwise then again there's ambiguity. How many variations do you have, 2A 2B, right? So that's why we just, with sequence number we tell that the first byte is this one, so that you can rearrange accordingly. You can understand how much, i- how much each packet contains, or where it goes. So that's why we suggest that the first data byte number is being given to you in the sequence number field. As a receiver, I need to know which packet, and if I receive a packet, in what chronological uh, order I have to arrange them. For that matter, sequence number is very important to me. Acknowledgement number is something that, uh, if I have received an acknowledgement number, that would be that, that field would be telling me that the data that I send next, you know, which data I have to send next. I mean, which data is being expected by the other side. Okay, so that's the acknowledgement number. Sequence number is which data byte am I receiving first in this packet. Okay, so that I can arrange it. Acknowledgement number is that which data byte I have to send next. Okay, now of course it's not just one data byte, it's going to be the whole packet. But with the first data byte number you will get to know that, if with the first data byte you have whatever the size, whatever the segment size that is possible to be sent, you can just send it, right? You do not have to worry about all that. But yeah, of course, with acknowledgement number you get to know which data byte is being expected from the other side from you. Okay, that those are the three rows. Then we come on to the fourth row. Okay, and here let's talk about the things which are being used right now. So first one is header length. Header length is of 4 bits, a 4-bit field. And now the mandatory size is 20 bytes, and the extended size could be 60 bytes. Okay, as much as 60 bytes. And with 4 bits we can just represent 15, 0 to 15, right? So that is 16 things we can represent with 4 bits. Now how are we going to represent 60 bytes from 4 bits is uh, a little bit of a thinker. And how are we going to be doing this? Now how we do it is, we say that the maximum size that we have to represent is 60 bytes. The maximum number that we can represent is 15. So what do we do is 16 divided by 15, that comes on to 4. Now we use 4 as a multiplicative factor for this whole thing. Okay, so like, you received, first of all, 20 is the mandatory, right? 20 is the mandatory size. Now if you receive, say you received 1010 in the header length, right? So that would 1010 is basically 10. Now 10 multiplied by 4, 40 bytes is the size of the header. Okay, that's what it suggests you. Then we have 6 flag bits and another field which is of 16 bits, window size or advertisement window. Okay, what, let's just talk about the whole row. So after header length there comes six reserved bits. Now what are these six reserved bits? Basically we thought that we are doing this right now, but there may be something that we may need to add in future. Okay, there could be some functionality, something, some sort of an upgrade, or let or maybe some sort of requirement comes up. So for that purpose we have six reserved bits in the TCP header, so that TCP is future proof. Okay, so that's why we added that field. Then there are six flag bits. First one is URG, that is urgent. Second is acknowledgement, ACK. Then PSH push, RST reset, SYN synchronize, and FIN fin. Okay, so the first one is URG. Now this flag bit, it's a flag bit, that means it's of one bit. So if URG is 1, that is, if URG, the urgent flag, is set, that just tells you that this segment contains urgent data. Okay, this segment contains urgent data. Now there's another field which is urgent pointer, which is in the fourth row, but I'm talking about that field as well here because it is relating to it. It's in the fourth row. It's a 16-bit field, the urgent pointer. And what it does is, if the urgent flag was set to 1, you get to know that this packet contains urgent data. Urgent pointer tells you which is the last urgent data byte. Okay, so consider if URG was 1, you get to know that okay, this packet contains urgent data. Now urgent pointer, so you start reading that data. Okay, till where the urgent data is, up until where, we need to know that as well. So consider if it was a 100-byte packet, and if the urgent pointer says that 20 bytes, okay, till 20 bytes, so that would mean that from the start till the 20th byte, that's the urgent part of the whole data packet, and the rest part is not so urgent. Okay, so that's how. So urgent flag suggests that urgent data is uh, in the urgent data exists in this packet. Urgent pointer tells you the last urgent byte. Okay, then we have ACK, that is acknowledgement. What does it tell you? Is that acknowledgement is there in this packet. Okay, acknowledgement is there in this packet. Then we have PSH, push. Now where push is something. Now there are a lot of different processes, like and a lot there are lots of different types of services or processes. Now consider you're sending some sort of a media, or let's just say a 4 gigabytes or media file you're sending. Okay, so what your transport layer will try to do is it will try to accommodate as much data as possible in a segment. Okay, then so that it can use the whole packet efficiently. Okay, and then it will make the second segment, and so on. So the complete segment size, it will try to use it. So that's that. But what if I am I don't want to do that? What if I'm not doing that? I'm just chatting with somebody on Instagram. Now I'm just sending hi, and I want that hi to be sent. Okay, I'm not waiting for the whole segment to be filled. I have sent a hi message, and I need that hi message to be sent. So that's where the push flag comes into play. That I we're just telling the segment, sorry, the transport layer, that you should do not wait for the whole do not wait for the complete segment to be filled, but send it right now. Okay, send it right now. So that's that. uh and like let me just check, or see. Okay. Yeah, it's completely attached. Then we have reset flag. So basically, if you receive a packet which has reset flag set as 1, or if you're sending a packet which is with the reset flag 1, if you're sending it, then you want the destination to know that we need to reset this connection. Okay, we need to reset this connection. I am resetting it right now. Okay, why? Because that can be for many reasons. If somebody else was trying to meddle in, let's hacker hai bhai, hacker hai, things like that. If any sort of problem occurs in the whole communication process, in the connections, then you might need to you might feel the need to reset the connection so that everything is again safe and sound. So for that matter, when if you receive a reset if you receive a packet with which has reset flag set as 1, then that means that okay, reset has to be done. You get to know about that. You can send that packet as well, that we're resetting it right now. So that's that. Then we have SYN, SYN. Now what does that do? SYN is something that we use for connection initialization. When we or establishment, okay, connection establishment. When we establish a connection, there are a couple of things that we do. So the first one would be okay, do I have the diagram? Because that way I would be able to tell things in a better manner. Okay. Yeah. So the first packet is sent as a request packet. Okay. Here we send a certain sequence. Okay, let's not talk about this SYN flag right now that much, because if there's a lot of other things that needs to be explained first, so that SYN and FIN are actually understood nicely. So for now, just know this, that SYN is used for connection establishment. It gets sent by both the sides, sender and receiver, or both can be sender as well. So I'm just saying sender and receiver. Let's just say A and B. Both the side have to send SYN, and that has to be acknowledged, and that's how we establish the connection. And the same has to be done for the FIN part as well, and FIN flag with the FIN flag as well, and that is used for connection termination. Then this is these are the 16 bits of the fourth row of the TCP header. Okay, in these 16 bits we just saw header length, which was of 4 bits. Then we had 6 reserve bits and these 6 flag bits. One was you urgent, then another acknowledgement, then push, then reset, then synchronize, then fin. Okay, SYN and FIN. Okay, then we have a 16-bit field in the fourth row, another 16-bit field in the fourth row, which is a window size or advertisement window. Basically, now what is this? If I am sending if I'm receiving data, okay, so with the window size I am telling the sender, I'm receiving, right? So I'm the receiver. I'm telling the sender that what is the amount of buffer space which is available to me right now. So if I am saying that it's I can say that everything it's completely available or it's partially available. So I will be suggesting that, okay, I'll be suggesting the size. So if I am saying all ones, that would mean that the complete buffer is available, right? And if I say 0, then that would be that no space is available. I can send anything else as well, like 20 bytes is available. So it can have any value. But now here's the thing, that it's just a 16-bit field. Does that mean that the maximum buffer size that I can advertise is 64 KB? Is that so? Well, no. Okay, because in today's world we do not have we do not use such old systems where 16 bits are you can just have like buffer space of 64 KB. You definitely have more than that. And what we do for that is we can use the options field. Okay, We can use bits from the options field to suggest what is, if you have more, then you can use a lot of bits from the options field, and then accordingly you can suggest that, okay, I have this much of buffer free, and you can send the data this much, that much. Then we have the fifth row, and this fifth row is divided into two fields again. The first one is checksum, that is of 16 bits. The another one is urgent pointer, this is of 16 bits. Now urgent pointer I already talked about, 16-bit field. Now with this 16-bit, now this urgent pointer is of 16-bit. What does it tell you? That with the 16-bit I need to specify all of the bytes. If the if urgent pointer may just say that, okay, so the urgent pointer can tell you that maybe the first, urgent pointer can tell you that the first 20 bytes is the urgent part of urgent data, or it may tell you that the first 40 bytes are the urgent data, or it may just tell you that the whole data packet is urgent. Okay, so what can we say from here is something more than that with 16 bits now I have to represent the whole packet, right? That means now here the packet would be called segment here, because we are at the transport level, right? So with 16 bits I need to be able to represent each and every byte of the data packet of the segment. So that definitely tells you that the segment size that we use right now is 64 KB. Okay, the maximum segment size right now that we use is 64 KB, and usually practically it's being used. So yeah, 64 KB is the segment size that is practically being used. I don't know if we can use more than that, but yeah, practically this is being used. Then we have options field, and this options field can be used for a lot of things. For one is timestamp, another one is window extension. As I said that you may need to you may have a lot of buffer size buffer available, so you can use you have just 16 bits. We use 14 more bits from the options field. Now this is like 30 bits, and with 30 bits you can definitely tell that 1 gigabytes is the size of buffer that you have available right now. So you may send that much data. I'm fine with it. Okay, so that's that. Then we have parameter negotiation as in like MSS. You negotiate MSS, right? Or buffer is definitely being negotiated. That this is the size of buffer that is available to me. Even if you can send more than that, don't send more than that, because I won't be able to store it. Or you can that has to be negotiated, and you may need to negotiate it again and again. That's why we have the window size advertisement window as well here. And yeah, and there's a timestamp. This timestamp is different from the timestamp that we had we have seen in the ICMP, which was to synchronize the time of different hosts in different countries, or maybe different like different time zones basically. And there's another one for padding. Now we also use options for padding. Why do we use that? Because in header length field we just have 4 bits, and 4 bits can has to represent 60 bytes. So we use 4 as a multiplicative factor. That's why the complete TCP header has to be the size of the TCP header has to be a multiple of 4. That's why if it's not a multiple of 4, we pad more data. Okay, to make it multiple of 4. Now if it could be what the size of the header, if you divide it by 4, the remainder would be the 0, 1, 2 or 3, right? And 0 is the one that we want. So if it's 1, then we add 3 more data bytes and we make it a multiple of 4. If it's 2, then we add 2 more and make it a multiple of 4, and that's what we do. And then we have data. Now this is the data. Now, this is where we have the data. Okay, above this we have the network layer, right? Sorry, below this, I'm sorry, below this we have the network layer. Yeah, and on the network layer another header is added, and that is the IP header, IPv4 header. And so when you receive it, you'll be having there'll be 2 headers. First one would be the IPv4 header, then there'll be TCP header, and above that data link header would also be there, which we add a certain SFD, start frame delimiter is added, or and also it also adds as like a tail end delimiter as well. So that's also added. So yeah, that's there. But data link layer 1 is actually not that important, as it does not really does a lot. So we have talked about each and every field of the header. Now I will be talking about the connection establishment, and there will be seeing the use of SYN flag, and then we'll talk about data transfer and data then connection termination, and with which will be almost done. Then there'll be retransmission, transition control. We'll come on to it. Okay, come to it just now. So first is connection establishment, and how do we do that? The first thing that you have to do is you have to make a request, and how do you do that? With SYN1. Then that request has to be acknowledged, and so let me talk again. Okay, so let's say A and B are 2 hosts which are trying to communicate. So A wants to initiate the conversation. So what A will be doing is requesting for the connection. How will it be doing that? 2 other flags which are being used here right now, and one is SYN, another one would be acknowledgement. Okay, ACK. So the first packet, the first packet, yeah, that would be the request. That would be the request packet, and in that you will be having SYN as 1 and ACK as 0, as you have not, as this is not an acknowledgement packet, because you have not received anything. You have you do not even have a connection established right now, so you have not acknowledged anything, and you assign the ACK as 0, that and by which you are saying that this packet does not contain any acknowledgement. But SYN as 1, that means that I am requesting for a connection right now. Okay, and sequence number, I sent a certain sequence number as well, that the data byte that I'm sending, okay, the first data byte that I'm sending is this one. Okay, and also I am I can suggest a lot of other things as well. I tell the destination that MSS is this much. Okay, that maximum segment size is this much. You send that. Okay, and you also tell the window size, the buffer size that you have available to yourself. That also you tell, you advertise. That's the request packet. Now this request has to be acknowledged, right? And acknowledged as well as it has to be initiated from the other side as well. The other side has to speak up as well. So what they will do is they'll also send you certain sequence number, that my first data byte number is this, and then they'll set the SYN flag as 1, ACK flag as 1. Why ACK 1? Because you are acknowledging that SYN which was sent by the other side, right? So this packet contains acknowledgement, and the acknowledgement number is next, because you received just a packet with the sequence number, with the certain sequence number. So your acknowledgement number would be the next number, which would be the first, would be the last byte number plus 1 of the data packet that you just received. So let's just say the other side sent the first data byte number as 521, and the size of the data packet was just 1 byte. Why 1 byte? Because it was just a request packet. Did not contain any data. Okay, so it was just a request packet. So it and the SYN was one. SYN was one. That's why, because of the SYN as 1 byte of data, one sequence number is consumed. Okay, so the sequence, the acknowledgement number that you'll be sending would be 522. That, okay, this is the next byte that I'm expecting. Okay, so the sequence number, you'll be sending a random sequence number. You'll be sending a SYN as one, that okay, I'm okay establishing a connection from my end as well, I'll be doing that. And acknowledgement number. And then MSS, you'll be telling the other side that okay, my maximum segment size that I have is 500 bytes, or anything. It can be anything. It may be lesser, it may be more. So whichever one is going to be the lesser one, the bottleneck, that's going to be used. And you'll also be telling the window size, okay, that I have this much buffer available to me. Now what happened is that you sent the SYN as one, you said the SYN as one, you said the ACK as one, which when that happens, both SYN and ACK are one. That just tells you that you are trying to establish the connection, and you have also acknowledged the request. So that would mean that this is the second segment, or it's the reply segment. The first one was the request segment, and this one, the second one, is the reply segment. Then when you send this, the reply, uh, then you are expecting acknowledgement. Okay, that okay, fine, now connection is done. And you need to, because you sent your acknowledgement with the last packet, now the other side has to send their acknowledgement as well. So what they do is they send you some sequence number, then they send you the acknowledgement number, because you also had a sequence number. You also sent a sequence number, and the reply packet was again of 1 byte, because it just contained the SYN as one. That's why we consumed one sequence number. I'm sorry, the reply packet is not going to be of 1 byte. That's stupid. It may be of anything, but one sequence number is only going to be used. That definitely means that you did not send any data. And whatever the size that the other side would be receiving probably is because of the header, right? So maybe because of that. So that's why. But we that's why just one sequence number is okay, sufficient. It's sufficient to do all this. So because of SYN one, we say that okay, once sequence number is consumed, and the other side is going to be working accordingly. But then it will have to send an acknowledgement. Now this acknowledgement again can be pure, or can be piggybacked. What is pure is it's just acknowledgement, and data is not sent. Acknowledgement is sent. So pure acknowledgement is where the acknowledgement is in the header, and piggybacked is where the acknowledgement is in data. Uh, Now, if it is in the data, then it'll be consuming data bytes, right? But if it is pure, then it will not be consuming data bytes. Now, if ACK is one, and no data is being sent, no data has been sent, and fin was 0 and SYN was 0, then 0 sequence number will be consumed. Okay, that's that. Then we come on to data transfer. After establishment, you'll be sending the packet with a certain sequence number, with a certain acknowledgement number. You'll be expecting some something from other side as well. If not data, then at least acknowledgement you'll be seeking. And you'll be also sending ACK. You're setting ACK as one, because you're sending acknowledgement number, that you're acknowledging something. Then from the other side, the same thing is going to be reciprocated. You can also send pure acknowledgement, you can also send piggybacked acknowledgement, anything like that can happen. And you can actually look at the diagram if you just google it basically. And yeah, if you feel like there's something that you may have to ask, you can definitely just comment or anything. What else? Comment, of course, right? That's that. And then come on to connection termination. Here we do the same thing that we did with SYN, but instead we use fin here. Why? Because firstly, the thing that so from both the sides, the fin has to be set one and sent, and acknowledgement has to be sent. And when that happens, the connection would be terminated. So it's all really similar to what happened with the sin. But let's talk in a bit more detail so that it's just ensured that we do not miss anything. So the first thing is whichever side would want to terminate the connection will set the fin as one and send the data packet. Okay, and while doing that, it of course ACK would be one. Why? Because just transfer data and you're definitely going to be acknowledging something. So sequence number would be there, ACK would be set, ACK acknowledgement number would be something, the fin flag would be set. The other side receives that. Okay, that okay. अलविदा कहने का टाइम आ गया है, तो अब okay, so that they're requesting for termination, connection termination. Now what can happen is you can send just an acknowledgement, not fin. This is you're going to do this when when you do not want to terminate the connection right now. Maybe you have more data to be to send or anything like that. You may have requirements. So you can just send the acknowledgement, or you can send the acknowledgement and fin together. That you send the acknowledgement with the you set ACK as one, you said fin as one. So that means that okay, you're also ready to terminate the connection. Okay, fin was one, ACK was one. Now you're ready to terminate the connection. And of course there's going to be certain sequence number, there's going to be certain acknowledgement number. Then that fin has to be acknowledged by the the side which sent the fin first. So basically, request for connection termination, reply for connection termination, then acknowledgement of connection termination, and it happens. Okay, now whichever side sends fin first would definitely not be able to send more data. Okay, whichever side sends fin first, sets fin first as one and sends the packet, means that they're requesting for connection termination. Now if you're doing that, you definitely know that you do not need it, so you do not have any data to be sent now. Okay, so we will not even allow you to send now. You set the fin, so whichever side sets fin as one first will not be allowed to send data whenever they do this. When the other side also sets the fin as one and replies with that replies to that request with fin as one, then the other side will also not be allowed to send any data. But before connection termination, we wait for a certain time, which is a time wait timer as well, which is it's known as time wait timer. For that amount of time, for this much amount of time we wait, so that if there's any packet in the network which is in the middle, it has been sent but it has not been received, so we wait for that everything just comes to wherever it is supposed to come. Okay, now that's that. With this we are done with the connection part, and most of the concepts of transport layer now basically not a lot left, and whatever like congestion control or something, this is not even that. It is definitely, I guess it's important, but I definitely think it's not even a head scratcher, seriously. So then we talk about retransmissions. Do I talk about it right now or should I take a break? Let's just continue. So then we talk about retransmissions in TCP. Now TCP uses SR plus GBN for flow control. SR is selective repeat, then GBN is go back in. It uses both. It uses a mixture. So what do we mean by that? Is basically it uses feature of both, whichever feature it likes, it uses. So like it has a window size of sender, it sets, so windows sender window size and receiver window size is equal here, which is definitely, in selective repeat it does that. And with that, of course, it can send out of order packets as well. But it uses cumulative acknowledgement, which gets used in GBN, go back in, whereas in SR, selective repeat, we use independent acknowledgements. So it uses cumulative acknowledgement. So that's TCP. Now we do retransmissions, and we will need to retransmit when something went wrong, right? Uh, so we retransmit if we do not get an acknowledgement. That means that whatever data that I sent was not received. Okay. So if I do not receive the acknowledgement, I retransmit it again. How do I know that I have to wait for a certain time? I wait for a certain time only, because I cannot wait indefinitely, right? So I would wait for a certain time, and if in that certain time I do not receive an acknowledgement, I retransmit that packet again. That's how retransmission happens. But to make it more efficient, that I do not want to waste so much of time, what I do is, we use this early retransmission method, where the thing is that if I send a data packet, okay, and it was selective, it was selective repeat kind of stuff. We sent a lot of them. We sent the whole window, and I receive, and let's just say these 4 packets are going, and the second packet was not received. Okay, so what is going to happen is, first packet is going to land there, then it will send an acknowledgement number. Second packet did not go, so it will not send an acknowledgement number, of course, right? But the third packet did go. It sends the acknowledgement number, which is going to be the same as the first packet sent. This so the third packet as well sends the same acknowledgement. This sends the same one. This sends the same one. This will send the same one. Okay. Now, when this happens, when the other side receives that 3 duplicate acknowledgement number has been sent to me, then it gets to know that I do not need to wait for the whole timeout timer. It will just get to know that yes, that data packet has not been received. I can retransmit it just now. So that's how you can make it more efficient, so that you do not so the other side, so you do not have to wait for the complete timeout timer, but you can transmit before that. Before that, what is before than that? But of course, early retransmission is not efficient. Okay. What if more than one packet was lost, and you received let's say 200 was the sequence number which got missing. So you received 200, and let's say 300 went missing, but you received 200 thrice, and you retransmitted 200. What about 300? You never got to know about it. So that's how it's kind of, it's not reliable. But we were using timeout timer. We did not used early retransmission instead of the retransmission with timeout timer. We are using that plus this, so that it becomes more efficient. So it's an update, right? Now these retransmissions, ICMP packets, a lot of ICMP packets, and like a lot of things. This all can may create a lot of problems in the network, and one of those is congestion. Now we mean that now congestion means what it means in English. Now it's in network. Basically, network would be congested. So everything would be, like we've seen certain situations where we have experienced that Geo is down, or Airtel is down, or Instagram is down, or Google is down. So what is happening? Congestion is there. Okay, so that's that. So sender should not dump the data more than the receiver can handle, or the network can handle. Otherwise, it causes unnecessary retransmissions, and that causes, again, congestion. To protect the network from heavy traffic, which can eventually cause crashes, TCP congestion control is implemented. Okay, so we need to control the congestion, and there's a TCP congestion control algorithm where we have three phases. First one being slow start, then there's congestion avoidance, and then there's congestion detection. Slow start is actually not slow, it is actually exponentially growing. What we do is we start from 1 again. What? Window size. Okay, if congestion occurs, we uh, assign 1 as the window size and then double it till we reach the half, the midpoint. Okay, so let's say the window size was 64 kilobytes. So what we're gonna do is this: we first we start with the slow start phase, and here we start with 1. That's why we are just calling it slow start. Otherwise, it's growing exponentially. We send 1 byte of data, uh, then we double it: 2 bytes, 4 bytes, 8 bytes, 16, then 32. We reach the mid 32. Then we grow it linearly. 32, from 32 with 33, 34. Now let's say congestion occurred here. Okay, and if congestion occurred here, so again we go into slow start phase. Start from 1 again. 1, then 2, then 4, then 8, then 16. Now, but congestion occurred at 34, right? So what we do is we divide 34 by 2. Now 17 is the point where we have to we set as the mid, because congestion occurred at 34. So now the new mid has to be 17, half of 34. So then 1, 2, 4, 8, 16. Now you've reached 16. Now you go 17. Okay, then 18, 19, 20. Let's say again congestion occurred. Okay, but this was detected as 3 duplicate packets. So you basically, if timeout timer expires, that means that the data packet was not received, and that would happen when congestion is there. Okay, otherwise there's gonna be no. Otherwise the site would have received the data. If they have not, and the timeout timer expired, that means congestion is severe congestion, and we need to start from the slow start phase again. But if uh, if it's the 3 duplicate packet ones, the timeout timer did not expire, that means we received 3 duplicate acknowledgements. We retransmitted again. Now again, if it should have reached by that, then right. So but it's not a severe congestion, it's mild congestion, or yeah, mild congestion. So here what we do is congestion avoidance. Basically, congestion avoidance is growing linearly. So let's say 20 was the window size when congestion occurred, but mild congestion. So mild congestion, that would mean that 3 duplicate acknowledgement were received, and you will grow now linearly. So 20 was the window size, then threshold would be calculated as 10, and from 10 you start 10, 11, 12, and so on. Okay, Now TCP has timers, uh, and a lot of different types of timers. First one is time wait timer, which I just said. Wait for the late packets uh, before closing the connection. How much do we wait? We wait for twice the lifetime. Now, lifetime of a packet is usually 3 minutes. It can be more than that as well, but we use 3 minutes uh, nowadays, which means in 3 minutes it definitely should reach the destination. Okay, and we wait for 6 minutes. That means before terminating the connection. Then keep a live timer. Keep a live timer, which is used to close the idle connections. Okay, that no data is being sent. There's a connection and which is just idle, so kill it. The name is keep alive, but it kills the connection. Okay, because it's saying that whichever one is alive, keep them. Then there's persistent timer. This persistent timer is like it's used if you were sending data and then you received an acknowledgement, and along with it the window size that was advertised was 0 bytes. That means no buffer space is available. So if that's the case, then you cannot send any data right now. So what the other side is supposed to do is whenever the buffer gets available, they should advertise their buffer that okay, now it's available. But what if it does not? So from your end as well, you try to uh, avoid uh, situations like this. I mean, you're responsible on your own as well. So if the other side does not send an acknowledgement in such a case, then you also have a persistent timer for which you wait, and after which you send 1 byte of data. And if 1 byte of data is received from the other side, at least then it will send you an acknowledgement, and also along with it, it will also tell you the window size or the buffer size which is available, and then the communication just resumes as it was before. Then acknowledgement timer is there uh, for both cumulative and piggybacked. Acknowledgement timer, basically how it is the timer where we use like if a lot of packets are coming to me, I wait for a certain time, and as many acknowledgements I receive, I send the as many data packets I sorry as many data packets I receive, I send the acknowledgement uh, in that timer. Basically, in that time, as many packets I received, I will send the acknowledgement of all of them together. Okay, so that's that. Then there's timeout timer, which was for the acknowledgement if acknowledgement is not received. Okay, acknowledgement timer is if the it's for the data that was received, you send the acknowledgement. Timeout timer is for if acknowledgement is not received and you need to send the data. Okay, that's that. Now we talk a little bit more about timeout timer, because it just sounds so much like a fairy tale. So that yeah, it gets done, but it's not so simple. Things are there. How would you know what should be your timeout timer? How would you know how much to wait? Right? Now, the ideal timeout timer should be uh, round trip time, right? Twice the round trip time, basically. But we'd say okay, fine, twice the round trip time. At least in that much time, I should get the acknowledgement. Round trip time is basically from one end to another, and from there to back again here. Okay, first end. That's round trip time. We wait for twice the round trip time, just for that at least in this much time I definitely should get an acknowledgement. But what should be the timeout timer? What if I'm using a timeout timer which is not really efficient? Maybe I'm just using a really really huge timeout timer which definitely delays stuff, because I'll be retransmitting. If the acknowledgement is lost, then I will be retransmitting. Sorry, if the data packet was not received and that's why the acknowledgement was not sent, then I will be retransmitting really late, right? And what if I what if I'm using a timeout timer which is uh, lesser than the round trip time as well? In that case, I will be retransmitting uselessly onto the network, and now it's an SR protocol, so I'll be sending like a lot of data packets as well. So that may lead to congestion too. So for that matter, I have to calculate the timeout timer uh, responsibly, or you can say I need to use this efficiently. Okay. So, algorithms for timeout timer computation. First one is basic algorithm. Second one is Jacobson's algorithm, and then there was some guy named Khan who modified it as well. Okay.